Okay. Yeah, this problem with the camera is that it stops recording after 30 minutes. Okay. Any questions for me? Yes.
What difference paper, this paper
Yeah.
and star?
Oh, this is a vector, right?
Yes.
What does this mean? What does that mean?
When come together.
Yeah, but it's a vector. How do you take the complex conjugate of a vector? Remember, it's an abstract vector. I haven't even told you what the vector is. Right? Remember, it's not the ordinary vector anymore. It's not some arrow pointing in some way. No. It's an abstract vector satisfying a bunch of axioms. How do you take the complex conjugate? It's not a number. You see what I'm saying? It's not a number.
Yes.
So how do you take the complex conjugate of a number, of something that you don't even know whether it's a number?
Convert K to block. So it's the AC.
Yeah, then you're using this definition, right? Yeah, so the answer to your question is that because it is not a number, it's a vector. Therefore, when you want to convert cat to bra, you need to give it a new notation. Because it's not the same thing as just taking the complex conjugate. You cannot even take the complex conjugate because the thing you're dealing with, the vector, is an abstract object. It's not necessarily a number. Right? So that's the answer to your question. It's a distinct, this thing is a distinct operation, distinct from just the usual complex conjugate. But of course, you're asking the question because there is a relationship. As you'll see later on, when you start to write your inner products and your vectors in terms of its matrix representations, then you convert this abstract language into matrices and the usual vectors that you're more familiar with. And then in that context, there's a relationship between dagger and complex conjugate. Right? So you probably have seen it before. That's why you ask this question. So for now, be patient. We'll get to it very soon. Okay. Good. Any more questions? Yes.
What is mean about lower back?
Say again.
Lower back.
Yeah. Remember, the goal vector right now is just the definition that you get when you take the dagger and then it will map it. It will convert your cat into a bra. Okay, so but on that alone, it's just symbol pushing. It's an empty definition, right? I just convert one symbol to another symbol. What is important is what it does. Okay, so that's a key point. At this point, it's just a symbol, it's just a new symbol. But what is important is this sentence over here, which is what it does. And why it is important is because it allows you, through these constructions, right? So this guy, these rules, together with the axioms of the inner product, it allows you to define the generalization of a dot product in vector spaces. It's what it does that is important. You understand? Yeah. So by itself, yeah, who cares, right? But graph space is important in physics because it allows you to carry out and talk about the inner product. That's the main purpose. Very good. So with axioms, we should of course do an example. And again, I'm going to use the simplest example of the real d-dimensional vector space. and see that what I'm saying over here is true. Turn on the AC. The AC. This is very hot in here. Are you guys hot? No? Who's hot? Are you hot?
No.
No, you just want to ask a question.
Ask a question.
Yeah.
Can I code it? Cat do better if I take a dagger on the bra space?
Right. So you're asking if I take a dagger on the bra, what do I get? Right? Is that what you're asking? Let me write it down. Right. So, so we have defined, thanks, this. Okay, so this is the definition. But now you want to ask, what is this? Right? And the answer is, as you guessed correctly, is that it will return you the cat. But this will take a little bit of a development. Right? So you know the thing in math is that you want to distill down to the minimum what are the basic assumptions. And then from there you deduce all the facts. Right? So this is a definition, but this will turn out to be a fact that you can deduce from the structure of your inner products and so on. Right? So, but we'll get to that. Okay? So this is a fact. This is an assumption, but this is a fact that you can deduce from one can deduce from inner products. In fact, I think you're going to prove it in your homework, I think. It's one of the homework problems. Yeah, it's one of the homework problems, I believe. Let me just check. I'm going to find it. I'm pretty sure it's one of the problems. Yeah. Okay. So let's do an example. Okay. So the example is, of course, just a dot product. Of real real vectors. Right? So, because I want to use the direct notation, I'm going to put a cat sign around the outline. So, for example, if I take the inner product of A and B, of course I can just say A dot B, but I will now use the direct notation. So, A bra acting on B cat is just going to be the usual A dot D. Right? And again, at this level, it is too much baggage. Right? So why invent a new notation when you have the old notation? And that is true. But once you have to do quantum mechanics, you discover that this notation is necessary. So let's do it. Right? So what are the axioms? Well, we're going to check, for example, that A acting on B plus C. Check, this is your first axiom, is in fact A acting on B plus A acting on C. Okay, and why is that so? Because this guy is A and B plus C. We've already seen when we worked out the basic axioms of the vector space, B plus C is just B plus C. And therefore, this will just be A dotted into B plus C. And this, you can work out directly, is distributed A dotted into B plus A dotted into C. Okay, just write it out and you can see directly. And then, in 2, is just A acting on, let me call it alpha times B, where now alpha is just a number, just so there's no confusion. This is just a number. And the question is, can I pull out can I pull it out? Okay, and the answer is yes, because alpha times beta, again, this is something we've done previously when we worked out the axioms of the vector space. Alpha times beta, B, is just alpha times B vector. Okay? And then you take this inner product, dot product, so A dotted in alpha B. And then again, you just write it out. And you can see that this is in fact alpha times A dot B. Okay, and which is exactly this guy. And then A3 is the following. So this is very simple. A, B, star. Well, A, B is just A dot B star, or they're real, so there's nothing to do here, it's the same thing. There's nothing to do. So this is in fact B, A, sorry, let me do it step by step. So A dot B, there's nothing to do, but I can swap, because it's just, ordinary multiplication when you write it all out. Okay? A1 times B1 plus A2 times B2 plus A3 times B3 and so on. And A1 times B1 is equals to B1 times A1. Okay, this is multiplication. So I can certainly write it out in any way I want. Bj ai, okay, which is just b dot a, which is of course just b a. Okay. So this part is very easy. And then finally, or almost finally, A4. What happens when you take A dot A? Oops, AA, according to our definition, is just A dot A. Okay. And here, if we write it out, is sum of AI times AI, which means you can write it as AI squared. So you're taking the sum of the squares of the components. And squared, because it's real, because A is real, all the components are real. Therefore, this has to be greater or equal to 0. And because, again, you're summing the squares of components. And because the components are real, the squares are strictly non-negative. It can be 0, but it cannot be negative. This is squaring something. Nothing can be, no real number can become negative when you square it. Okay? And therefore, it satisfies the fourth axiom. And finally, this is why I wrote it out explicitly, A dotted into itself is 0. Well, how can it be 0? Well, look at this. If it's a sum of the squares, then if it is 0, it means that every term in this sum must be 0. Right? So if this is true, then all the AI squares must be 0. All of them are the first component, second component, third component, all of them squared must be 0. How can that be true? It means that, and it goes both ways. Right? If this is true, then every component squared is 0. If every component squared is 0, then this is true. A dot A is 0. Well, what does that mean? It means that A is a 0 vector. Every component must be 0. So that's the definition of the inner product, satisfied by the usual dot product. It must be, this, like I said, this is a generalization of the usual dot product to the more complicated case. Now, when you allow, I should say, if you allow A and B to be complex, then you will discover that this thing will be non-trivial, that A3 will be non-trivial. And in fact, let me just say, if you're dealing with complex vectors, then you have to modify your definition. Instead of A dotted into B, you now have to take A star dotted into B. So what that means is the following. It means that you can write it in different ways. One, if you just write it out directly in terms of summation notation, in terms of the sum, it will be the I component of A complex conjugate multiplied by the I component of B and then sum over all the components. Or you can write down using the summation convention using the connected delta. So this will be AI. And then let me put a bar on top of it to show you this is star. Remind you that this is star, complex conjugate, and DJ. So this is the same thing. So for your homework, you will step through that this definition, if A and B are complex vectors, then this definition will be a good replacement for the definition of the dot product for real vectors, in the sense that this definition will satisfy the 5 axioms. Okay? And I should also mention that I should mention 2 things. One is that this is where the relationship between the dagger you've seen in matrix algebra makes contact with the dagger that we are introducing here. So in particular, when you write this down, you see that this is nothing but A dagger, because there's a complex conjugate here, dotted into B. Okay, so in this case, you can write it as an A transpose acting on B. Right? That's another way of writing the dot product. But here, you need a dagger, which means you include an additional operation of taking the complex conjugate, and that, in fact, is another way of writing the inner product. That's one thing to say. The other thing to say is that this, in fact, why I want to highlight this inner product in particular is because this, in fact, is this representation of inner products for all finite dimensional discrete vector spaces. So in some sense, all the abstract stuff that you do, as long as it is a discrete finite dimensional vector space, you can basically write it down in this way. Okay? So it's not supposed to be obvious right now, but as we go along, you will see that in fact, once you understand vector spaces in the form of complex d-dimensional or CD, right? What I'm calling is CD. Once you understand this case, it's often the case that the more abstract stuff will all become much more understandable because they're actually mapped into each other. There's a CD is essentially the concrete description of the abstract vector spaces, and its inner product. Let me just, I know my time is up, but let me just say two more examples of inner product here. So this is the first non-trivial one. We did the real inner product. This is the sort of the real, the first non-trivial example. The other example is if x and y are d by d matrices. Okay, so they can be arbitrary. So we already figured out that the space of d by d matrices over real or over complex, in this case we'll just deal with the complex case because it's more general. We will already seen, or rather you're going to prove in your homework that those form a vector space. Now it turns out that you can also assign an inner product to them. So that's really quite non-trivial, right? Because so far we've just talked about dot product, we've talked about the complex generalization, but now also for matrices, right? So that's a somewhat big departure from just what we've discussed so far. But I claim you can in fact define a corresponding dot product to them. What is it? I will define that I take the inner product of X matrix with Y matrix to simply be the trace of X hat dagger and Y hat. Okay? That's my claim. That this is a good definition of inner product of complex matrices, square matrices. Okay. And this in fact will show up repeatedly. The more you do physics, the more you'll see this definition show up. Even the theory of non-abelian gauge theory has an inner product of that. And then finally, we have the inner product between polynomials. If f of x and g of x are polynomials, in fact, they don't really be polynomials, but let me just focus on that example. Then it turns out that if we integrate them on some closed interval, where -1 to 1, it will turn out that you can define the inner product as just F star and G, and then integrate it over the interval. This is also a good definition of the inner product. Again, this is now a non-trivial generalization. Right? You used to think of inner product as, oh, it's just a dot product. No. Now, just from the set of rules, the axioms 1 to 5, as long as they satisfy these axioms, they make a good inner product. And so for your homework, you're going to show that these three examples that I give you, the CD, the matrices, and this integral definition of F dotted with G, F acting on G, all these three actually satisfy the same axioms. And therefore they all make, even though concretely they look different, they all actually are good definitions of inner products. Any last questions for me? No? All right. See you guys on Thursday.